Okay, so here's a small video doing some clarification, and it's related to a question one of you asked. I think Hanneke asked this question about how the integration actually follows through in this case. So if you remember, we were trying to calculate the spectrum of synchrotron emission, and then we had this scenario where the particle is moving in a curved trajectory, and then you get this narrow pulse. Um, Around the time when the particle is moving towards your direction, and then we try to calculate the spectrum of that pulse by taking the Fourier transform of the electric field and squaring it, and the electric field basically came from the retarded potentials of the charge. Those were the retarded fields. And while taking the Fourier transform, you get an integral which is of this form, right? So you have an exponent here. T prime is the retarded time, so T prime minus n is the um, position vector from the particle to the observer. R naught is the position of the particle by C. So this basically is the phase of the electromagnetic wave, right? So this is kind of the phase of it, and so it's inside the complex exponential. And then we had this another factor which turned out to be a perfect derivative, right? And then we said, oh, okay, you can integrate by parts. Now it turns out that the details of the integration by parts are omitted in every textbook that I could find. So I worked this out for myself, and it's unfortunate that it's omitted because um, it's not obvious. There's a little bit of subtlety here, and I think I have the right answer here. Okay, so we have integration by parts. One function is this complex exponential, the other function is this derivative. So I'm going to call this f of x, and I'm going to call this g of x. And then you have this scenario where the first term of f of x times g of x is going to be f of x times the integral of g of x. Okay, so the integral of the derivative is the function itself. So the first term is just going to be this function f of x, which is the complex exponential, times the integral of g of x, which just gives you this term here in the bracket, because the integral and the differential cancel each other, the two operators. Now the second term is again the integral of g of x, which again just gives you the term here times f dash of x. Okay, so the derivative of f of x, and that's inside the integration sign. So the first term is written out here. Here's the second term, and the second term is going to be the integral of g of x, which is just going to return this quantity in the brackets, times the derivative, the time derivative of f of x, and all of that is inside the integral sign here. Okay. Okay, so what do they actually look like? Well, first of all, notice that I've extended the limits of integration from minus infinity to infinity. And you make a infinitesimally small error by doing that. Now, in reality, of course, the particle is moving in a circle, so there's no such thing as minus infinity. But what we're trying to do is we're trying to just take the Fourier transform of one of those pulses, right? And if you look at that pulse is so narrow because of relativistic beaming that at at a time which is very is far removed from time equal to 0. So when t prime equal to 0 is where the pulse is centered, and if you go away from it, then the pulse goes to 0 very quickly because of extreme levels of relativistic beaming. And so you don't make a big error by just extending the limits to minus infinity to infinity. So I've done that here. Okay, so what does the first term look like? Well, the first term is just this complex exponential times this term in the brackets, the geometric term, and that goes from minus infinity to infinity. Now the second term is the integral of the, well, I have to take the derivative here. So you get the exponential back, and then by the chain rule, you should take the derivative of what is inside the bracket. So that is going to be I omega times the derivative of this quantity, right? So the derivative of this quantity with respect to time is 1 minus the derivative of this quantity here. Now this is just the projected distance of the particle along the vector n hat, right? So the time derivative of that is going to be just n hat times beta, where the time derivative of this is just the velocity of the particle in the direction of the observer, right? So that's what the time derivative is. So you get 1 minus beta dot n hat, which is nothing but kappa, right? So the kappa and the kappa inverse cancel out. Okay, so that's the second term, and that's what remains. So why does the first term go to 0? Why do we disregard the first term? Well, let's have a look at this. We need to take this term and go from minus infinity to infinity, right? So let's just look at what the terms really look like. Now, n cross beta. So just assume that for a moment now, forget that the particle is actually going in circles. We are only interested in that narrow pulse, right? So you might as well imagine that the particle has a slightly curved trajectory, uh, and you're basically extending the limits to go from minus infinity to infinity. And when t prime equal to 0 is when you actually see that narrow pulse of radiation coming towards you. And as you go away from the t prime equal to 0, the angle, the velocity vector of the particle makes with the line of sight is just large enough. It's very small, but it's still large enough that you just don't see radiation from the particle. Okay, so that's the scenario you have in mind. So if I basically write this out as t prime going from some value, I don't know, just take some value, um, call it alpha, let's say. So it'll just take it to go from minus alpha to alpha, and then take limit as alpha goes to infinity, right? So that's what I'm doing. So let's look at the terms here. So t prime minus n dot r naught by c is basically going to be of the order, um, this term is going to be of the order the parallel velocity times t prime, right? So this whole exponent is going to be of the order e to the power I omega t prime 1 minus beta parallel, right? That's the rough value of that exponent, where v parallel is the velocity along the sight line to the observer. So again, I'm assuming that the particle is very far away from the observer. So v parallel is kind of a quasi constant value through the trajectory which I just described. Now, for a highly relativistic charge, K inverse, so remember K is 1 minus n hat dot beta. So when beta approaches 1 and n and beta is in the same direction as n hat, which happens at t prime equal to 0, 1 minus n hat dot beta goes to 0 basically, right? So K inverse will go to infinity. So that is why you get that really narrow pulse, because K inverse is going to infinity. Now notice that, sorry, I shouldn't call this K, kappa. Now notice that the kappas cancel out in this integral, but you still have a kappa inverse here. So this whole function is really dominated by the behavior of kappa inverse, because kappa inverse has almost like a pole at t prime equal to 0, right? So kappa inverse is going to be an odd function, an even function, first of all, and it's going to be very highly peaked around t prime equal to 0, because it'll be of the order 1 over an extremely small number, which is going to 0 as beta goes to 1. So what does this first term look like? Well, it's going to look like, when you go from, take these limits, all the even part of it is just going to cancel to 0. So you only get the odd part. So from Euler's formula, only the sign of this complex exponent remains. So 2i times sine omega t times 1 minus beta parallel. And then, this factor this is going to be an even function, right? And so we need to take this limit as t prime goes to infinity. Now, if t prime goes to infinity, this whole factor is going to be extremely small. Again, this comes down to the fact that kappa is extremely peaked. So kappa is extremely peaked function at t prime equal to 0. And then kappa inverse is extremely peaked. And if you go to very high values of t prime, this whole function goes to an extremely small value. So the upshot is that the first term, is almost 0. You can neglect this. And once you neglect the first term, then the second one is what remains. So you're neglecting the first one in lieu of the second one, because the second one doesn't have the same behavior, right? I mean, there's kappa and kappa inverse cancel out. So the second term actually is not highly peaked if you look at it. The second term just goes as n cross beta. There's no kappa in the second term. So the second term is not this almost a delta function kind of term. It's only the first term which is like that. So the second one actually contributes most of the power into the most of the energy, so to say, in the Fourier transform. The most of the spectral power comes from the second term. There's very little spectral power coming from the first term, and that approximation and that integration by parts is what leads to the expression we had, where we just had this integral left. So thanks, Hanneke, for asking this question, because I had not fully appreciated this before, and it turns out that it's not there in any of the textbooks. So which was surprising. I thought that some of this would be mentioned in some of the textbooks, but I couldn't find it in any of the textbooks we're using for the course. But anyway, it's a very subtle point. It's good to know. You don't have to lose your sleep over it. Uh, but if ever you get stuck in some derivation when you're doing research, and then you're like, oh, wait a minute, how did that work out? Then you have it here. But yeah, don't lose sleep over it. It's fine. This is a pretty subtle point, and it's not straightforward to actually figure out what the how the derivation progresses.